So today, we're going to introduce material from chapter 9. Excuse me. The topic being chemical quantities. And this is the only chapter that's going to be covered for exam 5. All right, so what do we mean by chemical quantities? Well, up to this point, we've learned our chemical symbols, we've learned how to write compounds and how to name the compounds from their formulas. We've learned how to put those compounds and elements into equations and balance the equations. We've also learned how to determine the number of moles of a compound if we have a mass of the compound. Similarly for elements. Now what we're going to get into is using the balanced equation to follow the progress of a reaction from a given amount of reactants to how much product we should expect. Okay, that's what we mean by chemical quantities. All right, so a little bit of review concerning chemical equations and the balanced chemical equations, by the way. Okay, a balanced chemical equation tells you only the number of moles of a reactant that enter the reaction with any other numbers of moles of reactants and how many moles of products are produced. So the ratios in the coefficients of the equations, the ratios of those coefficients determine the ratios of the moles of the reactants to each other and the reactants to the products. For instance, if we simply react oxygen gas with hydrogen gas and we produce water, right? We know how to balance that. We need 2 here, 2 oxygens. Now we need 4 hydrogens. Okay, now that the equation is balanced, we know that we can look at it 2 different ways. We can say 4 molecules of hydrogen react with 1 molecule of oxygen to produce 2 molecules of water. A more useful approach is to look at this in terms of moles, because moles gives us a handle on mass. And I'll show you how that works in just a minute. This would be 4 moles of hydrogen gas react with 1 mole of oxygen gas to produce 2 moles of water. And depending on the conditions, temperature and pressure, this could either be a gas or a liquid. Under standard conditions, it will be a liquid, of course. So that's what a balanced equation tells us. Relative numbers of molecules or relative numbers of moles. There's another example. For this example, we have C2H5OH, which is ethanol, ethyl alcohol, the kind that you can drink and get drunk on. But you can also burn it. And if we combine it with oxygen in a combustion reaction, and the reaction is complete, we will get carbon dioxide and water in those ratios. In other words, we get 1 mole of ethanol reacts with 3 moles of oxygen to produce 2 moles of carbon dioxide and 3 moles of water. Okay. It's exactly what I just said. And those are the two ways that you can interpret the reaction. The ratios, if we look at the ratios, there's a 1 here, 1 to 3 to 2 to 3. And that ratio, once the equation is balanced, that ratio is fixed. 1 to 3 to 2 to 3 will be the same for that reaction no matter what the conditions. And it will be the ratio in terms of molecules or moles. It's always numbers of compounds or numbers of elements. All right, so one of the steps in producing pure copper is that copper ore follows this reaction. All right, so we have copper sulfide. Oops. Yeah, it's not behaving. Right? C2H, and this is a solid. Right? So while we're here, what is the name of this compound? We know that sulfur is in the chalcogen group. It's with oxygen, so it's going to have a 2- charge. That means this total has to be 2+, and this one has to be a 1+. So if we name this compound, we have to call it copper 1, because copper can have more than one charge. Copper 1 sulfide. Okay. We can react it with this compound. Right? Similar situation. This one's a 2-, so this one has to be a 1+. So this compound would be copper 1 oxide. So if you're given a problem that says copper 1 sulfide reacts with copper 1 oxide to produce copper metal plus sulfur dioxide. Right? Remember, this is a type 2 compound, that's a type 2 compound. This is type 3 because both are nonmetals. So that's the way you would name them. Okay, now that we have that, we have the reactants and products written correctly. Then we need to balance the equation, right? So that's the balanced equation, but how would we get there? If we use the budget system, let's do that first. If we use the budget system, that means we got to count for copper, sulfur, and oxygen. On this side, we have 4 coppers. We have 1 sulfur and 1 oxygen. And on this side, we have 1 copper, 1 sulfur, and 2 oxygens. Okay? So remember the trick? This is an element. We're going to save it to last. So we're going to balance sulfur and oxygen first. Sulfur's already balanced. Oxygen, we need 2 oxygens on this side. Okay? So there's 2 oxygens there, and that leaves 4, 5, 6 coppers. Okay? So now we need a 6 in front of the copper to give us 6 coppers. And we're balanced. Okay? So now that we have a balanced equation, and by the way, if your equation is not balanced, then you're dead in the water. You cannot go any further. You have to establish the correct ratio of reactants and products in order to do anything from now on. All right, so now that we have a balanced equation, and let me remove some of this clutter. We don't need that now. Now we can proceed with the concept. Once we balance the equation, how many dozen copper atoms could be produced from a dozen molecules of sulfide? And 2 dozens of oxides of copper. Okay, they're referring to the sulfide here. So if we have a dozen molecules of sulfide, 1 dozen, and we're determining how many dozen copper atoms, right? That's where we're headed. A dozen molecules of sulfide and 2 dozens of oxides. 2 dozens. Okay. Remember, we're still in numbers of things. Dozens, that's a number. How many dozens of copper, right? So if we have 1 of these, there's the 1, there's a 2. This means we have 6 dozen copper atoms. Okay. Now, once we know that, also how many moles of copper could be produced from 1 mole of sulfide and 2 moles of oxide? Well, we just changed the units. We're still talking about numbers of things. So 1 mole here and 2 moles there produce 6 moles here. Okay? The point of this exercise is to emphasize the fact that we're dealing in numbers of things, not mass, not volume, numbers. Let's see, I don't think we're going to need this one again. Right, we're on to something else. Okay. So we've established that the ratios of the coefficients are best understood in terms of moles, relative moles of each of the reactants and products. So this balanced equation, I showed you the reverse of that equation, where you reacted hydrogen and oxygen and produced water. In this case, we've got water, and we're going to split it into hydrogen and oxygen, and that's very easy to do. But this is our equation now. We're going from water to hydrogen and oxygen gas as separate products. And this can predict the numbers of moles of the reactants that will yield a certain moles of products, or the number of products required to, the number of products that will produce from a given amount of reactants. Okay, so in this case, we can say that 2 moles of water yields 2 moles of hydrogen and 1 mole of oxygen. But we could also say 4 moles of water would yield 4 moles of hydrogen and 2 moles of oxygen. The ratio is the important factor there. Once the equation is balanced, then we can scale up and down. We could say 1 mole of water could produce 1 mole of hydrogen and a half mole of oxygen. We've still got the exact same ratio. That's what's important. Okay. All right. So the mole ratio that we derive from a balanced equation can be used as a conversion factor. I'll show you how that works. Let's see if there's any more on this slide. Example, okay. So if we have this reaction where, I have to give me some more markers. There we go. Let's see, sodium silicon fluoride. Sodium silicon fluoride. That's right. Yep, that's a solid. And that plus sodium metal, and this equation is balanced. React this with sodium metal, and we can produce silicon, pure silicon, and sodium fluoride. Okay, let's be sure it's balanced. All right, we have 6 sodium over there, 4 plus 2 is 6, 1 silicon, 6 fluorine, 6 fluorine. Okay, it is balanced. Now, the question is, how many moles of sodium fluoride will be produced if 3.5 moles of sodium is reacted with excess? So we're saying we've got all of this we need. There's no limitation here. And we're given 3.5 moles of sodium are reacted. Okay. The question is, how many moles of sodium fluoride will be produced? All right. So here's how you do that. You use your coefficients as conversion factors. And here's how it works. There's where we're starting from. 3.5 moles of sodium. We want to convert dimensional analysis, just like we did early on in the semester. We want to convert that sodium, cancel that sodium, and give us sodium fluoride as our answer. The ratio here is coefficients. So we have a 6 for sodium fluoride and a 4 for a sodium. So the sodiums cancel, and 6 times 3.5 divided by 4, they should have already done it for us. All right. All right, next slide. There we go. So there's our conversion factor. This is the mole ratio of that product to this reactant. Okay, and that should give us 5.25 moles of sodium fluoride. All right, we're going to have to, I'm going to have to dig for another marker. All right. Now that, okay, so we have another example. That was just one example where we can go from this reactant to that product. But we are not confined to reactant product direction. We can go backwards. We can go from product to reactant. Or we can go from product to product. All we need is that coefficient ratio. So here we have an example, propane, C3H8. Okay, reacted with oxygen, and they've been kind enough to balance the equation for us. Yields 3 carbon dioxide plus 4 water. Okay, now what's the question? How many moles of carbon dioxide? How many moles of carbon dioxide are formed when 3.74 moles, 3.74 moles of propane are burned in excess oxygen. Right? We got plenty of oxygen. It's like burning it in the air. There's plenty of oxygen. We just want to use up all of this and make those products. But we also want to know how much carbon dioxide is produced from this reaction. Right? So here's where we start. 3.74 moles of propane. And our conversion factor has to, and this is moles, and leave us with carbon dioxide. I don't always write moles in here because it's understood, but the ratio here is always moles to moles for our purposes. Okay, so what's the ratio? Well, let's see, 3 carbon dioxide and 1 propane. So 3 times 3.74, which should be, let's see, 12, and 1 is 21, 22, and 2 and 9 is 11. 11.22 moles of carbon dioxide. Now let's see if they agree with me. Yep, 11.2. Well, let's see. I should have rounded it off. Right? 3 significant figures, 3 significant figures. All right. So that still went from reactant to product. We need an example that goes some other directions. But for now, what we're going to do is use the ability to convert moles to moles to determine masses of product that can be produced if you know the mass of the reactant. Okay. First rule. Actually, there's a rule before that. Write your elements and compounds correctly and position them in the equation as reactants or products. If you cannot write the compounds correctly from their names, then you can't go any further. Right? The only way to balance an equation is with chemical formulas. So once you've got the formulas in the equation written correctly, then you balance the equation. And we've learned how to do that. Then you take the masses of your reactants or products, depending on which ones are given to you, convert them to moles. Because if you have a reaction, right, it produces, from reactants you produce products. If you have mass here, you are stuck. You cannot move anywhere in that reaction with a mass, because the balanced equation is relative to numbers of things, of moles. This has to be converted to moles. Once you convert to moles, then you can move anywhere you want to. All right? That's crucial. Once you've got moles, then you can set up the conversion factor based on the coefficient ratios and determine how many moles of the other reactant or products, whatever the case may be. Once you find out the number of moles that can be produced, for instance, as a product, and if the question asks for the mass of the product, then you've got to take the moles of the product and convert them to mass again. And we have learned how to do that. All right. So this process of going from amount of one substance and finding the amount of the other substance in the reaction is called stoichiometry. we're following the process to find out how much product we can produce, or if we know how much product we want, how much reactant we need to produce that much product. Okay. All right. We're going to talk about limiting reactants in just a minute. When we say one is in excess, that usually means the other one is limiting. That is, it runs out. But hold that thought until we get to it. Okay, let's say we have this unbalanced equation. Let's see, we have, easier to read it up there. We have chromium, and we have reacted with oxygen to produce Cr2O3 solid. Now we know that's chromium, that's oxygen. What do we call this one? Well, it's right there on the page. But this is a -2, so -6 total, that means +6 over here, that means +3 there. So that's why it's named chromium-3 oxide. It's a type 2 compound. All right, now let's get on with the problem. How many grams of chromium-3 oxide can be produced from, so we want to know grams. If we have 15 grams of solid chromium, 15 grams of solid chromium and excess oxygen. Okay, so that means we've got plenty of this. We can use all of that to produce this. All right, here's what you do. You have to convert that to moles. So how do we convert that to moles? Dimensional analysis, right? We need to cancel the grams and leave us with moles. And whenever you see grams and moles in a quotient, that's molar mass. So what's the molar mass of chromium? We go to our periodic table. 52.00. Rounded off to 2 places. That's the molar mass of chromium. Okay, so we divide. Let's see. Oh, that's not balanced. I'm getting ahead of myself. We have to balance that equation, don't we? This one should be fairly easy because there's an element, there's an element. We need 2 chromium and 3 oxygen. Right? How do you do that? We use our fraction trick. So 3 halves would give us 3 oxygens. Now we get rid of the fraction, multiply by 2, and that makes 4 here, that makes 3 there, and that makes 2 here. So now we have our balanced equation. Okay, so that's going to be 4 here and 3 there. Okay, now that we have a balanced equation, we don't have to stop. We can still determine the number of moles of chromium, 52 into 15. So I don't have to get my calculator out. Let's see, we should have a step in there. There we go. Oops. I don't think, oh, that's the molar mass of chromium oxide. Okay, so we will need the masses, the molar masses of each of our. So this one is 152 grams per mole. This one, oxygen, is 32 grams per mole. And this one is 52. We've got it already. Okay,
Now we can move ahead with our conversions. So chromium converted will yield 0.288 moles of chromium, right? So now that we have moles, think of the balanced equation as having great walls built. You got a wall here, you got a wall here. You cannot get over that wall, you cannot go under the wall unless you're moles. I guess if I use the analogy correctly, if you convert to moles, you can dig under the wall and get to the other side. So now we know that we have this many moles of chromium. We need to convert that to chromium 3 oxide. So the ratio is 4 here and 2 there. So we need 1/2 of that value, 0.144 moles of Cr2O3 are produced. Okay, so that's what we did right there with this operation. Now we want to convert this back to mass. So we need another conversion factor that will take moles of chromium 3 oxide and give us mass. And that's where this value comes in, 152 grams per mole. And that should be 21.9 grams. So what we're saying is, by these calculations, we have shown that 15 grams of chromium burned in excess oxygen, that's a combustion reaction, will produce 21.9 grams of chromium 3 oxide. There we go. Or you could do like this and put it all in one single step. Just chain your conversions together. But it's a little harder to follow that way. I think this way is easier for most students, and it's the way I choose to do it too. But it does give you the same answer. Okay, so here's another problem. Let's see what we can make of this one. Okay, tin-2 fluoride is added to some dental products to help prevent cavities. Tin-2 fluoride is made according to the following equation. All right, so it looks like that one's balanced. Let's put it up here and check it to be sure. Remember, fluorine, hydrogen fluoride, excuse me. Hydrogen fluoride is in aqueous solution. I think it said there are 2 of them, correct? Yep. Yields tin-2 fluoride. Solid? No, aqueous. Pardon me. Aqueous plus hydrogen gas. Okay, let's see. 110, 110. 2 hydrogens, 2 hydrogens, 2 fluorine, 2 fluorine. We got a balanced equation. Okay, how many grams of tin-2 fluoride? How many grams can be made from 55 grams of hydrogen fluoride? 55 grams of hydrogen fluoride if there is plenty of tin available. So this is excess. Okay. So what do we need to do? We have to convert, after the equation's already balanced, we have to convert hydrogen fluoride to moles. So we need a molar mass for hydrogen fluoride. What would that be? Well, hydrogen is 1.01 grams per mole, and fluorine is 19. So that's 20.01 grams per mole. Okay, so now we can convert that many grams to that many moles. All right. So we just divide this into 55 and, oh, they did it in one step. All right, they're using 3. I rounded off to 2 places, right? So if I'm going to do it myself, assuming my calculator is going to work, okay, 55, enter 20.001. So I get 2.7486 moles. Now notice what I've done here. Since we're not doing this in one step as on the slide, now I'm going to keep all my decimals. I'm not going to round yet, because when you go step by step by step, if you round at every step, then you could end up with some substantial rounding error. That's one of the advantages of stringing all of the calculations together in one operation. Then you have you don't have the rounding errors that could be built in. But if we do it this way, I keep all my decimal places until, and this is going to be hydrogen fluoride, until the end. So now we need to convert this to 10,2 fluoride, right? That's a 1, right? Don't forget that whenever you have a compound or an element here, if there's no number in front of it, the number is 1. And HF is 2. So we just need to take half of this value. It's already in my calculator, so I'm just going to take half of that, 1.3743. Okay, and this is moles of SNF2. Now we just need to convert it back to grams. Moles on the bottom, grams on the top. We haven't calculated that yet, right? What is SNF2? What's the molar mass of that compound? Well, let's see, 10 is 118.71, 118.71 for 10, and then 2 times fluorine, 19. And so 118.71 and then 19 times 2, add them together. 156.71 grams per mole. Okay, so we multiply that times that value, and we get 215.3686 grams of 10,2 fluoride. But we need to round it, right? For this is a multiplication division rule for significant figures. So we just need to find what's the smallest one. We started with 3. So we want to round to 215 grams of 10,2 fluoride. All right. And there it is. Okay. So when you're dealing with stoichiometry, you need to lay out your plan, and you need to approach it step by step. Be very methodical about your calculations and reasoning. Every time you make a calculation, ask yourself, is the answer reasonable? Am I headed in the right direction? Because there are multiple steps that have to be accomplished before you can get to your final answer. All right. Let's see what's next. Oh, we have another one. Okay, I'm game. PCl3 plus 3 water. Looks like they balanced the equation for us already. H3PO3, H3PO3. Now, if this reaction is going to be in water, that means this compound is going to be in solution. Right? So that's aqueous. So what's the name of this one? This one is phosphorus trichloride. It's a type 3 compound. But what's that one? If it's in aqueous solution, PO3 is phosphite. And the ites become us's when we're naming acids. So this would be phosphorus acid. Okay? Just a little review. It doesn't hurt. Plus HCl, which is also in water. So what would that one be? Okay. No oxygens, so we start the name with hydro. And hydrogen chloride would be the gas, but dissolved in water, ides become X, hydrochloric acid. Okay, now let's get to the problem. What mass of water is needed to completely react with 20 grams of phosphorus trichloride? So we need to know mass of water. The only reason that these are over here is because they're part of the equation. And the equation can't be balanced unless you have reactants and products. But once the equation is balanced, we can do this operation and not even consider that side. Okay, so we're going to go from here to here, but that's grams. So we need what? We need the molar mass of phosphorus trichloride. So phosphorus is 3097, okay, and 3 chlorines, 3545, I do believe. Yes. Okay. So 3545 and 3 times that, and then 30.97 plus 137.32. 137.32. So divide that into 20, and we get 0.1456 moles of PCl3. Now we need to convert that to moles of water. And the ratio is 1 to 3. So we just need to multiply 3 times that. 0.4369 moles of water are required for that reaction. Okay, now we convert it back to grams. Right, what's the molar mass of water? We've done this so many times. It's 16 plus 2 times 1.01, which is 18.02. So multiply that times 18.02. We get 7.8736 grams of water, but we have to round it to 3 places, right? 3 places. So we're going to go here. Those drop out 7.87 grams of water. All right, there we go, there we go, there we go. There we are. Okay.
as is my custom, we start simple and we get more complicated for each exercise. So let's see if we can make sense of this one. We've got a balanced equation here with an unknown element x. 6x. They're telling us it's a solid. B2O3. 2B2O3. And that's a solid also. By the way, what is that? They're both nonmetals, so it'd be diboron trioxide. Yeah. In fact, I think there's a special name for this called diborane. But you wouldn't know that one, and that's okay. B4X3, B4X3 solid plus 3XO2 gas. Okay. So the question is, what is X? Well, we know X is an element, right? Because it's here all by itself. We've been given the balanced equation, right? We can check it out. There's 6X there. There's 3 plus 3X there. There's 4 borons, and 6 oxygen. So that's 2 times 3, 6. Okay, so we know it's balanced. So how are we going to figure it out? Well, this compound is complete. We know what that one is, right? We can tell the molar mass of this one, right? Oh, there's more to it. Sorry. If 175 grams of X, okay, reacts with a diboron trioxide to produce 2.43 moles of this. 2.43 moles, 2.43 moles of that as a product. What's the identity of X? Well, how do we identify an unknown element? There are only 2 ways. If you know the atomic number, the number of protons, it's easy. You just follow the periodic table until you find the right number of protons. We don't have access to that in this scenario. What we do have, though, is the second possibility. The molar mass of elements is usually unique. There are occasions where they're very close and experimental error could cause an overlap in your results. But most of the time, if you know the molar mass, then you can determine the element. So we're going to go for molar mass here. Well, what do we need for molar mass? Right? That's my abbreviation for molar mass. We need mass per number of moles. Right? We have the mass right here already. We need to find out how many moles that represents. Then we can calculate the molar mass and discover the element. So we need to know the number of moles of that one. Okay? Well, we have this many moles of that product, and we have a balanced equation. Why don't we just do 2.43 moles of B4X3 and convert it to moles of X? Okay? So the ratio is 1, and this is 6. Right? So 2.43 times 6 is 14.58. 14.58 moles of X. Right, we cancel that one. Now we have the values. We have 175 grams for 14.58 moles.
So let's divide that into 175. 12.00 grams per mole. Okay. Now what we have to do is go to the periodic table and follow along left to right, top to bottom until we find 12 grams per mole, the molar mass. And the nearest one we can find is carbon. Carbon at 12.01 grams per mole. Right? Nothing else comes close. So that is most likely our element. Here we go, and there we go, and there we go. Okay. That was a lot simpler than it looked. Okay. What's next? Okay. Now we're going to start talking about excess and limiting reactants. First, we're going to start off with a stoichiometric mixture. What is a stoichiometric mixture? The stoichiometric mixture is one that contains exactly the amount of reactants, 1, 2, 3, 4 reactants, exactly this right amount of each one, so that when the reaction is complete, they're all gone. There's nothing left over. They're exactly perfect ratio for the reaction to proceed to products with nothing left over of the reactants. That's a stoichiometric mixture. So here we have the famous Haber-Bosch process. Nitrogen gas and hydrogen gas yields ammonia. Okay. Visually, you'll see that we have hydrogen here, and we need 3 hydrogen molecules for every 1 nitrogen, just like that. They're surrounded by these dotted red lines. And this is mixed mixture is a stoichiometric mixture because we have exactly the right amount of each one of the reactants for the other. And that will produce 2 ammonia molecules for each one of those reaction blocks. So the stoichiometric mixture produces only products and no reactants left over. All right, but here's the reality. Every time you measure out reactants for a reaction that you're going to conduct, remember every measurement has error, experimental error built into your measurement. You can never get exactly the right amount of reactants so that you have a stoichiometric mixture. That's a theoretical value. You will always have at least one of the reactants be limiting. In other words, it's a smaller amount than you expect, and it runs out first. That's the limiting reactant. And this is the artist's rendition. In this case, if we pair up the nitrogens with the number of hydrogens you need, we can only have 3 perfect groupings. And we have some nitrogen left over. In this case, nitrogen is excess and hydrogen is limiting. All the hydrogen will be consumed and you'll still be left over some nitrogen. Okay? All right. So there's our example, and we're just hammering this point home. Excess means that there will be some of that reactant left over. because the limiting reactant ran out. And when that happens, the reaction stops. All right. So once you have a balanced equation, and you're given amounts of the reactants, and we're going to keep it simple. Say you have two reactants. You're given amounts of each reactant, either moles of each, mass of each. If you're actually given a value for each reactant, then you know 99% sure that one of them will be limiting. One of them will run out. So we need to find out which one is limiting, because the limiting value of that reactant will determine the maximum amount of product that can be produced. So here's an example. Methane and water react to form products like this. We have methane and water will produce hydrogen plus carbon monoxide. Okay, let's see, is it balanced? We have 4 plus 2 is 6. Yep. 1 carbon, 1 oxygen. That equation is balanced. Okay, a stoichiometric mixture would be, you'd have 1 methane, 1 water molecule gives you 3 molecules of hydrogen and 1 molecule of carbon monoxide. Or you have 1 mole of methane, 1 mole of water gives you 3 moles of hydrogen gas and 1 mole of carbon monoxide gas. That would be a stoichiometric mixture. If all of these are gone, now we have nothing but product. Okay. In this example, if we count up the molecules, notice that we have 1, 2, 3, 4, 5. We have 5 moles or 5 molecules, same ratio, and we have 3 moles of water, right? So which one is limiting? This is a 1-to-1 reaction. So 3 moles of water only needs 3 moles of methane. That means we have 2 moles of methane in excess. Okay? Now, how much product will be produced? Well, 3 moles of water can produce 3 moles of carbon monoxide because they're 1-to-1. Water to hydrogen is 3-to-1. So we can produce 9 moles of hydrogen. And that's what that picture shows. But we will also have 2 moles of methane in the same reaction vessel with our products. We'll have some methane left over, but the water will be completely used up. All right, so this is excess, water is limiting. All right, so this is just a step-by-step doing a stoichiometric problem where you have limiting reactant. How do you know you have a limiting reactant? The first clue is that you're given exact amounts for each of the reactants. If you don't have a limiting reactant, it'll give you an amount for one, and it'll say the other one is excess. So the one that's given will be the limiting one because it can all be used up. So you write your equation and balance it. then you position the known amounts next to your reactants and do the conversions. Convert the masses into moles. Okay, now this is a general operation. So if we're given, let's back up. Say we're given X grams of methane and Y grams of water. You would convert this to moles. X prime moles and Y prime moles for water. Then you would take this one and convert it to one of your products, right? So you would say, how many moles of hydrogen can be produced from all of this? Then you would take this and say, all right, how many moles of hydrogen can be produced from that? Okay, and you compare these two. The reactant that is limiting is the one that produces the fewest number of moles of product. So if this one is less than that one, this would be the limiting reactant. Okay? That's what we're getting at. And then if the product says, all right, the question asked how many moles of hydrogen could be produced from this reaction, you already have your answer. It's this one. But if the question asked how many grams or what's the mass, then you would take this one and convert to grams to answer the question. All right. So here we have another example. Yes. This is going to be a limiting reaction problem, limiting reactant problem. Okay, so we have 10 grams of aluminum react with oxygen. What's the mass of the product that we produce given the molar mass of aluminum oxygen? Okay, the product is aluminum oxide. So we have aluminum metal plus oxygen gas yields Al2O3 solid. Now, we're given the product here, but does that make sense? Right? Aluminum has a fixed charge. It only has 3+ charge. Oxygen has a -2 charge. So 3 times -2 is -6 plus 6. Yeah, that's good. We've written the compound correctly. Okay, now we can balance the equation. Well, let's see. We need 3 oxygens over here, right? And we need 2 aluminums. Now we've got to get rid of the fraction, right? Okay, so we multiply by 2. And by the way, the equation's already there balanced for us. I'm just going through the procedure so that this is going to be a 4. This is going to be a 3. And this is going to be a 2. And that's what we should have there in our balanced equation, and we do. Okay, now that we have the balanced equation, what are we given? 10 grams of aluminum. Right? And 10 grams of oxygen. Right? That looks like stoichiometric. I mean, if you're not well versed in what to do next. Okay. We're given the molar masses for each one, 26.98 for this one. So we're going to convert this to moles. Well, the question is, how There's no question there yet. Let's see, it must be down. Here we go. Oh, what mass of product? Okay, what mass of product? There we go. So we convert this to moles, right? So the mass was given as 26.98 grams. So we divide 26.98 into 10. Is 0.3706 moles of aluminum. And while we're at it, I'm just going to go ahead and convert to aluminum oxide. The ratio here is aluminum 4 and 2 aluminum to oxide. So we just need to divide that by 2. 1853. 0.1853 moles of aluminum oxide. Okay, that's how much aluminum oxide could be produced from this much aluminum if all of it is used up. So now let's go to this one. 10 grams of oxygen, right? 32 grams per mole. So say 10 divided by 32 is 3125. Moles of oxygen. Now we're going to convert oxygen to aluminum oxide. So we still have the 2, and this is 3. So 2/3 of that value is 2083. So if all of the oxygen is used up, we could produce 0.2083 grams, moles of aluminum oxide. With 10 grams of aluminum, we can only produce 0.1853. This is the limiting reactant. That makes this one excess. Okay. So the question is, how many grams of aluminum oxide can be produced? All right, well, there we go. 706. Okay, we've done those calculations. Okay, now we're going to convert them to aluminum oxide, each one. And we find the comparison gives us aluminum as our limiting reactant. So we take the value derived from aluminum here and convert it to convert this to grams of aluminum oxide. Let's see, do they give us the molar mass of aluminum oxide? We have to calculate it. Okay, 2 times aluminum. Aluminum is 2698. Well, we already knew that right here. 2 aluminums and 3 oxygens. 3 times 16. So what's the molar mass of aluminum oxide? 26.98. 2 times that, and 48 for oxygen, because 3 times 16 is 48. 101.96. So 101.96 there. And let's see. Times 18.8955 grams, but we've got 3 significant figures, so we have to round it off to 18.9 grams. That's what we can expect from this balanced equation, this reaction, and these absolute amounts of our reactants. There you go. This is just a cautionary note. You can't simply add the total moles of all the reactants to decide which reactant mixture makes the most product. You have to always think in terms of what's the maximum amount you can produce from this one, what's the maximum you can produce from that one, and compare. And the one that produces the least amount in terms of moles is the limiting reactant. And that's the one that determines when the reaction stops. Okay. So which of the following reaction mixtures could produce the greatest amount of product? Each involves the reaction symbolized by this equation. All right. So let me erase this and we'll move on with that slide. Okay. So with this balanced equation, two waters, yeah, 2 moles. The ratio is 2 moles of hydrogen, 1 mole of oxygen produces 2 moles of water in the stoichiometric ratio. So, but if we have 2 moles of hydrogen and 2 moles of oxygen, how much water can we produce? Well, for every one of these, you need 2 of those, right? So this one would need 4 of those. Or we can look at it this way. For every 2 of these, you need 1 of those. So if we use that up, we've only used up 1 of these and we have excess oxygen. So with 2 of these, you can produce 2 moles of water. Right? So for the first one, we can produce 2 moles of water. All right. For the second one, we have 2 moles of hydrogen and 3 moles of oxygen. 2 and 3. We have a similar situation. 2 needs only 1. So we have 2 left over. And we can only produce 2 of those. So again, 2 moles of water can be produced because hydrogen is limiting and it determines the amount of water. How about 2 and 1? We have 2 moles here and 1 mole there. That's a stoichiometric mixture. We could theoretically produce 2 moles of water. How about 3 moles of hydrogen? All right. In this case, 1 mole of oxygen needs 2 moles of hydrogen. So we're going to have 1 left over and all the oxygen is used up. Well, 1 mole of this produces 2 moles of water. So we produce the same amount of water with this mixture, only now oxygen is limiting. Each produces the same amount of product. All right. Okay, so we've got the Haber-Bosch process again. N2 plus 3H2 yields 2NH3. Okay, so if we have how many grams of ammonia can be produced? So grams of ammonia. How many grams of ammonia can be produced from the mixture of 3 grams each of nitrogen and hydrogen? 3 grams here and 3 grams there. All right. If you're given amounts of reactants, you can be pretty sure that one of them is going to run out. So what we have to do is find out which one's limiting. So 3 grams of nitrogen will be how many moles? Well, nitrogen's 14.01, so this is 28.02 divided into 3. That's 1071, 0.1071 moles of nitrogen. I'm going to go ahead and convert this to ammonia. So we have a 1 here and a 2 there, which means 0.2142 moles of ammonia could be produced from that much nitrogen. How about hydrogen? What's the molar mass of hydrogen? Well, it's 2.02. 1.01 for each hydrogen, 2.02. So 2.02 divided into 3 is 1.4851 moles of hydrogen. Okay. Now we just need to convert hydrogen to ammonia. So we have 3 here and 2 there. So 2/3 of that value is 0.9901, 0.9901 moles of ammonia. Right? So it's easy to see from this calculation that these amounts of reactants will produce only that amount because nitrogen is limiting and hydrogen is excess. So we need to find out how many moles, well, how many grams of ammonia. So 0.2142 moles of ammonia is how many grams? We need the molar mass of ammonia. Right, so let's see, ammonia will be 14.01 for a nitrogen and 3.03 for the hydrogens. 1704 times 0.2142. Let's see, and 2 times, and 17.04 times 3.6488 grams. Or we have to round it to 3 places. 3.65 grams. There you go. And those are the steps we used to find out which one is limiting and then converted the limiting reactant to product. There it is, 3.65 grams. All right, one more problem that we have to deal with in chemistry. This is particularly troublesome for chemical engineers, right? Because chemical engineers are tasked with the job of producing the most possible product from the least amount of reactants. That's how their company makes money. And the key to that conversion is percent yield. What we've been dealing with up to now with our balanced equations are, this is the ideal situation. In other words, 100% of that nitrogen was converted into ammonia. It doesn't happen that way in the real world. You lose things along the way. You lose things to, let's see, purification process, right? Because they're all in a mixture together, and you got to get the product out. If you've got some reactant left over, you got to separate the product that you want from the mixture. So you lose something in the purification. The other possibility is side reactions. suppose that the conditions you set up for the reaction are not quite right for the reaction you want. You may produce a small amount, hopefully, of the wrong kind of product, right? It happens every day in the internal combustion engine, right? When you put octane, gasoline, into your tank and it goes through the carburetor, well, actually now it's fuel injectors, mix it with oxygen and burn it inside your engine to get energy from it, the reaction is incomplete and or produces side products, right? Normally what you would expect would be octane plus oxygen would produce carbon dioxide and water. That's ideal, that's complete. But what it usually produces is things like carbon monoxide. And there are other reactions in here that can occur with nitrogen. Nitrogen can occur in those extreme conditions. You don't just have oxygen in there in your engine. You have nitrogen because it's sucking in air, and air is 79% nitrogen, right? And it's only 21% or about 20% oxygen. So this nitrogen and some of the oxygen can combine and produce nitrogen oxides, right? So these side reactions produce products that you don't want. So that's why most cars now have catalytic converters in their exhaust train. And that takes these incomplete combustions and finishes the job and leaves them to either these or back to nitrogen gas. Okay, so those side reactions are a problem. There are other things that can happen, but we don't have time here to discuss them. What I'm getting at is the percent yield is a measure of efficiency. You know, how much of the product can you get out of a reaction based upon what you expect to get? And it's a very simple calculation. The theoretical yield is based upon the stoichiometry of the reaction itself. And the actual yield is what you are able to isolate and measure at the end of the reaction. So if we take the actual yield, usually in grams, and divide it by the theoretical yield, would also have to be in grams, times 100, we get percent yield. Okay? There you go. So for this example, the percent yield of product, find the percent yield of product if 1.5 grams of SO3 is produced from 1 gram of oxygen and excess sulfur. All right, so here's our equation. 2 sulfurs plus 3 oxygen gas yields 2 SO3. And we're given 1.5 grams of SO3 is produced. So 1.5 grams equals actual yield. And we started with 1 gram of oxygen and excess sulfur. Right, so we're already told that this is a limiting reactant. So what would happen? What would you produce from 1 gram of oxygen in this reaction? How much is the theoretical production there? Well, we need 1 gram of oxygen converted to moles. Right, so this is 32 grams per mole. 32 and hit the inverse, it's 0.0313. 0.0313 moles of oxygen produce how much SO3 under ideal conditions? Oxygen SO3. So you have 2 of these, 3 of those. So 2/3 of that is O208 moles of SO3. Now, what's the mass of that SO3? Moles. And we need the molar mass of SO3. Let's see, sulfur is 3207. And we need 3 times 16. So let's see what we get. 32.07 and then 48 plus 8007. Okay, times 0.0208. 1.6681 grams theoretical. So percent yield is equal to 1.5, that's actual, divided by 1.6681 times 100. $89.92. 89.92%. Let's see, we're limited to 3 significant figures, right? So it's actually 89.9%. There you go. All right, so we have some rounding error in there. It happens. But that's how we calculate percent yield. Now you can also use percent yield to work backwards. Say you're a chemical engineer and you want to know how much oxygen that you need in this reaction in order to give you exactly 1.5 actual yield. In that case, you would need to know what the percent yield is. Then you can calculate what the theoretical value is, because only the theoretical works in a balanced equation. And then you could work backwards, just reverse your direction and find that you need 1 gram. So it can work in both directions. Okay, I think that's what this problem is about. And I believe this is the last one in slide, and we should have time to do this one. So let's get our balanced equation first, which is phosphorus plus, I'm going to leave the phases out for simplicity's sake, yields 4PF3. Yeah, okay. What mass of phosphorus do you need to produce 85 grams of PF3? PF3, if the reaction yield is only 64.9%. So in this case, we want to find out what that is, but we can't get there unless we determine how many moles of this are theoretically produced. Right. So we're going to use this to determine how many grams of PF3 do we need to be theoretically produced in order to work backwards. So 64.9, we can approach this two different ways. This is 85 grams actual. Right? And this is 64% actual over theoretical. So this would be 64.9 grams actual for every 100 grams theoretical. Now, why can I say that? Because percent means parts per 100 or grams per 100 grams. This means 64.9 grams actual yield for every 100 grams theoretical yield. Okay, that's why I can say that. And it needs to be inverted in order to cancel this one. That's why it's upside down. Okay, all right. So this will tell us how many grams theoretical we need for that product. 85, let's see, let me back up. 85 grams, and then times 100 and divide by 64.9. 130.97. 130.97 grams theoretical. Okay, now we can use the equation, but first we have to convert that to moles. Okay, so what's the molar mass of PF3? Well, let's see. One phosphorus is 30.97. And then 3 fluorines. So let's see. 19, 3 times that. Oops, try that again. 3 times. And then 30.97 plus 87.97 grams per mole. So we need 87.97 divided into 130.97. 1.4888. And this is moles of PF3. Now we want to convert that moles, PF3, to P4. The coefficients are the conversion factors. 4 for this one, 1 for that one. So we divide 4 into that. 3722. 0.3722 moles of P4. Now we can determine the mass. All we need is the molar mass of P4. So phosphorus is 30.97. So molar mass would be 4 times 30.97. $123.88 grams per mole. 123.88 grams per mole times 0.3722. 46.1082 grams of P4, and we have to round it off to
3 places. So it'd be 46.1 grams of P4.
There we go. That's how it's done. In those steps, my way. Okay, we got to do some canceling here. And we end up with 46.1 grams. That's how much phosphorus is needed in order to produce this much phosphorus trifluoride if this is your yield. So what are we doing? In the process, we're losing 45 and 44, about 44 grams of product we're losing to something else that's going on in the reaction. Either we didn't purify it correctly or there's side reactions. Or one thing that I haven't covered was most reactions can also run in reverse. We've seen that in a couple of slides where we had hydrogen oxygen going to water, and then next slide we have water going to hydrogen oxygen. Well, these reactions can theoretically reverse themselves. So if that's the case, then some of this might go back to that and leave us without some product, those reversible reactions. We don't have the time or the expertise in this course to discuss that particular problem, I don't think. Let's see. No, we're not gonna discuss equilibrium, chemical equilibrium in this class. You have to take the general chemistry version to get that. But it's enough for you to know that these reactions could run in reverse and rob your products of some of their mass. They could go backwards. Okay, I think that's the last slide. Let me see. Yes. Okay, so we can stop the share.